Y'all, today we're going to be talking about point slope equations for lines. We've seen this equation a few times. We've talked about linear equations like slope-intercept form quite a bit, but I just wanted to use this new strategy we have for shifting, compressing, inverting, or flipping our functions and try to do it with something that we do know, something like a line. So just to review, we had our parent function for a parabola or a quadratic equation to be y equals x squared. Remember, the parent function is just telling you the most basic way to represent a family of functions. So in this case, we can see here that our graph will actually just give us a parabola right at the origin. Something that looks like that. You can create it by chart to verify, throwing in maybe x between -2 and 2, and you'll see that your outputs will give you a line like that. You know what, let's just go ahead and do that real quick. If you're feeling okay about this, you can actually skip ahead. Just want to make absolutely sure that we know how to get this graph from this table. So when x equals -2, we square that or multiply it by itself, we get a y equal to 4. We can see that by just putting in our -2, squaring it, find out that's just -2 times -2, or y is equal to 4 when x equals -2. So that's our first point. So we could go 1, 2, 1, 2, 3, 4. We go backwards 2, up 4. Notice how it goes, how it follows perfectly with our function. So when x equals -2, y equals a positive 4. We can do that again for a -1. Square it, we get 1. So go backwards 1, up 1. We're right here. We square 0. We're right along the origin. We square 1. We get a 1. Oops. Square 1. We get a 1. And finally, when we're over here at 2, we square it, we get a 4. So if we decided to do x values in between all of these, maybe x equals 1.5, we'll find that if the y, or the output, will put our point right on this quadratic function, or on this parabola in the case of the graph. So we then realized, hey, we can actually shift this thing. So we can start off with our parent function, knowing that the a in front compresses it, stretches it, or flips it upside down. Found out if we subtracted an h from here, this h corresponded to a horizontal shift, and then our plus k would finally give us the vertical shift. So if we were to kind of take this parabola right here, shift it over, maybe stretch it a little bit, we'd be able to see, and I'm going to do an extreme case here, I'm going to flip it upside down, so our a is negative. So because we have that upside down, we know a is less than 0. We shifted our vertex over h units, and we shifted upwards k units, like so. So that actually means we can represent our parabola with the vertex h comma k, because we shifted it over from the origin, which up here is 0, 0. So we found out that we can actually do this to all our functions. That's what we talked about last time. We had our absolute value function. Y equals the absolute value of x. We had the cubic function, y equals x cubed. We had our rational function y equals 1 over x, and we also had our, what was the last one? So we had our cube, our absolute, our rational function, and we had, completely blanking right now. So the absolute value of x cubed 1 over x. Oh yeah, we had our exponential function, of course. So we found out that if we follow the same exact ideas right here, so h pairs with the x, or the input, a multiplies our parent function, so if we're looking right here, we see that a is multiplying what our parent function was. And then finally, k is added to the overall parent function, is added to the parent function. So in other words, we take our x squared, we shift it over h, we multiply it by our a, but then this overall function right here, which is just a more complicated version of our parent function, is then being added to, then has a k added to it, like so. So we found out that we can do it to here, subtract h from the absolute value sign, subtract h from the x within the cubed, subtract h from the x in the denominator, and finally subtract h from our x in the exponent. The k is just added to all of these, and finally the a is just multiplying our parent function each time. So we can also do this with a linear equation. So for our linear equations, we're used to saying, oh, well, y equals mx plus b, and so we know m is the slope, b is our y-intercept, learning a bunch of tricks about this. But if we wanted to have a more general strategy in order to graph our line given maybe a point in the slope, we can actually do this by a very similar idea of looking at the parent function, figuring out how it's stretched and how it's shifted. So our parent function for linear equations is just y equals x. So our first step is to figure out where the horizontal and vertical shift are. So we have our y. We're going to wrap parentheses around our x and find out that just like over here, we're subtracting our h from our x. So this will be a graph that's shifted over h units. Next up, we want to include a vertical shift, so plus k. So that's going to shift it up and down, the whole entire function. And then finally, we need to multiply our parent function by a in order to figure out how much it's stretched or compressed vertically. So in the case of a line, so with our parabolas, we got skinnier and wider for the stretches and the compressions. For our line, the stretch is going to be, the vertical stretch is going to be bringing it closer and closer to vertical, whereas the compress is going to be closer and closer to horizontal. So what we should know about the steepness of the line is that that corresponds to the slope. So a is actually going to be our slope. H is going to be our horizontal shift, and k is going to be our vertical shift. So I'm actually going to rewrite this a tiny bit in order to use values that we're more familiar with. So m, and then I'll just leave the h and the k. So if we're given a point on our line, we're given the slope, we can actually figure out what our linear equation looks like just by knowing the shift and the slope that we've been talking about right here. So if we were to make a general sketch of this thing, we'd see that given a point h and k on our line, can actually use our rise over our run to represent the slope. So just a small example I'm going to do right in this corner. Find the equation of a line which goes through the point - 7, -8, and has a slope of -4. So this, if we know our parent function, we know how we can intuitively show how it's shifting, then we actually don't even really need to do much other than put in the values. And you can see I've already color-coded it to match up with this. So we know our slope is -4. We know our h value is 7, our horizontal shift. And we know that our k is going to be -8. So plus a -8, I'm just going to put down a -8. And that's actually what our equation is going to look like. So one thing that might be a little confusing is, well, how are we shifting it if we're just given one point? But we have to keep in mind we're always comparing it to our parent equation. So if we're looking at our parent function, let me clarify that, parent function, it goes right through the origin with a slope of 1. So what you're basically doing is taking this origin point and you're moving it in this direction, and then you're adjusting the compression or the stretch to accommodate for that -4. So because we know it's negative, this thing flips upside down. It gets a little bit steeper, and then we move it backward or forward 7 and down 8 units. So it might look something like, our new line might look something like this, where our line flipped upside down and we actually have that horizontal movement of 7 and the vertical movement of -8 to move that point all the way down to here. So just some good building some more intuition about why these equations work the way they do. There's always a reason for these. I know we've been thinking a lot about kind of the tricks and the way to remember, all right, slope is rise over run, k is usually the y-intercept, but when we start thinking about it like this, we don't have to remember as much because we're knowing how these functions are actually created. So if you're still not super comfortable with that, don't worry, we're still going to have some more activities dealing with these shifts, but this will be really helpful once we start looking at more and more complicated functions.